So today we're going to talk about computational geometry. Computational geometry is sort of a merger of two different fields that a lot of people end up getting exposed to. Algorithms is something that people often study in university. And there's a lot of different things you cover in algorithms. Often you talk about graphs, you talk about matrices, you talk about whatever else. But you very rarely actually see algorithms applied to geometry. This isn't exactly the same as graphics, which does use some aspects of algorithms to apply to geometry. When I talk about geometry, I'm referring to the really classical things you think of as geometry. Points, lines, polygons, line intersections, enclosing points, whatever else. Today we're going to talk about a few different and doubles, but in particular, in some of the things we'll look at very soon, there's a couple different changes you'll have to make with how you implement them, because there's a lot of different edge cases that can happen with floating point arithmetic. The next most important thing that we will talk about is something that I'm sure a lot of you saw coming, a line, but not actually a line. What we really need to talk about is a line segment. In geometry, there's often a little bit of confusion coming into it from an outside point of view, where in real life you often talk about lines as having endpoints, but in geometry, a line is actually an infinite line, and a line segment has endpoints. So we're going to talk about line segments for this video. So how do we represent a line segment? Well, it turns out that's also very, very easy. All we need are two endpoints. Two endpoints are enough to represent a line segment. So we can represent our line segment with a simple struct consisting of 2 points. That's all we need to do. So next, we need to think about some fundamental operations that we could use for computational geometry. So graph theory, when we use algorithms, we often have operations such as iterating through all the vertices adjacent to a particular vertex that we give as input, or checking if two vertices are adjacent. Things like that. With arrays, we have things like checking what the value is at a particular value in the array. With geometry, we want to do things with points and lines. One thing that we could do, say, is check if 3 points are collinear. That's almost one of the fundamental operations that we're going to use, but we're actually going to do something a little bit stronger. The thing that we're going to program is given 3 points, whether they form a left turn or a right turn. And these 3 points are given in a particular order. So it actually has meaning to say that it's a left turn or a right turn or a straight line, which is the collinear case. So this cube represents our right hand. And we're going to use this cube to demonstrate a little something called the right hand rule. First off, out of the top of this cube, we're going to extrude our thumb. This is our right hand, and our thumb is pointing upwards. Now we're going to open up our fist and let our fingers face forward. So now we've got our fingers facing forward and our thumb facing upwards. And let's look at where our palm faces. So our palm faces this way. This is what we call the right hand rule. Given 2 of these coordinates, so given where our thumb is, and then where our fingers point, we can figure out where our palm points. This may seem really, really dumb, and maybe not too useful, until you realize that it turns out the right-hand rule applies to a bit more than just our hands. It also applies to the result of something called the 3D cross product. Now, we don't actually need to go jump in and look at the formula for the 3D cross product right now. If you've seen it before, great. If you haven't, doesn't matter. So first, let's come back and look at our 3 points. What's really going on here to tell if this is a left turn or a right turn is we have to compare 2 different vectors. So the first vector is an arrow from the first point to the second point. And the second vector is an arrow from the second point to the third point. And really, all we want to do is check. If we bring this vector over here and draw it here instead, is it aligned or is it not aligned? So here we can see, because we had 3 points in a line, the vectors are aligned. So we don't have a turn. all we're really checking is there an angle right here? What if the points aren't in a line? What if they're not collinear? What if our points are 1, 2, 3? Obviously this is a left-hand turn, but why? So now, if we draw our vectors, the first one looks like this, and the second one looks like this. And then we take this second vector and move it over here, and then we look and we see the angle here sort of turns to the left. You could say this is a positive angle, and a positive angle means a left-hand turn. The reason I call this a positive angle isn't just because it's the orientation used typically on like the unit circle and the Cartesian plane, where everyone talks about positive angles as being counterclockwise. We actually have a reason for that. And that is because if we take the right-hand rule, we stretch our thumb upwards, so directly towards us on the screen, and we put our fingers in the orientation of the first arrow, then our palm should be facing in the direction of the second arrow. That is, it matches a right-handed angle, meaning it's a left-hand turn in this case. That's how we use the right-hand rule. But this doesn't really actually tell us how to compute this. We really want to know how to actually come up with a result. So what is the result, and how do we compute it? So in order to get the result, we're going to use something called the 2D cross product. If you are really familiar with the three-dimensional cross product, you may have noticed that what I just said, where you take your thumb and point your fingers and then look at where your palm points, that's actually an example of the 3D cross product. And in fact, the 2D cross product is a special case of the 3D cross product, where we point our thumb off the screen. So this maybe doesn't help you if you've never been exposed to the cross product before, but it shouldn't matter too much. All you really need to know is, if we call the first vector v, and the second vector u, and each of these vectors, since they are one point minus another point, so the coordinates of this minus the coordinates of this individually, so the x-coordinate of this point minus the x-coordinate of this point, and the y-coordinate of this point minus the y-coordinate of this point gives us v, and likewise the same thing with these 2 points gives us u. Then, in order to get the 2D cross product, what we do is we take v x times u y minus u x times v y. And that's all we need to do. This number, if it's positive, means we have a left-hand turn, and if it's negative, means we have a right-hand turn. And again, if you haven't been exposed to the cross product, just take this as a primitive operation that we're going to use. This is very easy to compute. We just need to plug in some numbers and do a little bit of arithmetic, which the computer can very easily do for us. And then we're going to use the result to tell whether it was a left-hand turn or a right-hand turn. Now we actually need to implement this. The first thing we need to do is we need to have some sort of representation of a vector, except a vector is equivalent to a point. So we could code up a vector, or every time we wanted to use a vector, we could just use point. That's what we're going to do. So we're just going to use point as a vector. So the next thing we need to do is we need to actually be able to compute the vectors. In order to compute the vectors, we need to be able to subtract points. To subtract points, it's pretty easy, but to make it nice, I'm also going to add an operator overload. Also, because we should have done this, I'm going to add a quick constructor for both of these. Alright, and now we can compute vectors. So how do we actually use the vectors? Let's create our function that we're going to call the winding. So this winding is going to tell us whether points 1, 2, and 3 form a left or right turn, or if they don't form a turn at all. So first let's create our vectors. Next, all we need to do is take the cross product of these two vectors. And it's very, very important to note that the cross product takes two values, and the order of those values matters. It will actually give the opposite answer if you feed them in the wrong order. So it's very important that you take the cross product of v1 cross v2. Now, we actually need to implement our cross product before we can really think about how we're using this. So let's go and quickly add that formula as a function. So, as a reminder, how we use this result from the cross product is, if the result is positive, it's a left-hand turn. If the result is negative, it's a right-hand turn. And if the result is 0, there's no turn. The points are collinear. They're in a line. So really, what we'd like to do is we'd like to return the unique values for each of these numbers. It would be nice to, instead of returning a positive number, a negative number, or 0, just return 1, 0, or negative 1. Because we don't really care about the magnitude of the value itself. So this is just a really hacky way to do that. It will return the result normalized to 1, 0, or negative 1. So now, there's actually lots of other different primitives that we could implement, but we actually have enough primitives at this point to solve a problem. So why don't we solve a problem first? So the problem we're going to try and solve is called the convex hull problem. The convex hull problem is not too hard. So to understand, first we sort of need to understand what a convex hull is. So given a set of points, or given a list of points, or given an array of points, we want to compute the convex hull of the points. One way you could visualize this is by imagining each of these individual points as a thumbtack that sticks out a fair bit, and you put them all in a corkboard. And then you take a large elastic, and you stretch it out with your hands so that it's around all of the points, and then you let go of the elastic, so it shrinks to surround the points as tightly as it can. What would this elastic look like in the end? For this particular set of points, this is the shape the elastic would take on. It would take only the points on the very outside, but it doesn't necessarily take just the leftmost point, just the rightmost point, the topmost point, and the bottommost point, but it takes all the points that form convex angles. So in actuality, the shape of this elastic, after we've released it, is a polygon. So there are many definitions of a polygon, but in this case, all we really need to care about is the fact that a polygon is a sequence of points. So it is first this point, this point, this point, this point, and so on and so forth. We could represent the sequence as a vector, a linked list, an array, anything. It's also important to note that it's a cyclic list. So it doesn't really matter where the list starts, just so long as it contains all the same elements in the same order when you wrap around at the beginning. Something important to note is that there's sort of two different things that you might want to care about. So the convex hull includes also points that lie on these lines. So if there's a point right here, it would also include that point. The elastic would be touching that tack. However, we don't necessarily need to include those. That point doesn't give us any new information. So we have an option when we implement these to include them or to not include them. That's all we really need to understand for the definitions. So let's do a couple careful observations. So the first question we should ask ourselves when we see this problem is, do I know anything that's in the convex hull? We just saw an example where there were a lot of things that weren't in the convex hull, but is there anything that's really easy to identify and say, this point is in the convex hull? And it turns out there is. Just looking at this image, you might be able to identify that this point is in the convex hull. You might even be able to identify that all the points that are in the convex hull, but let's just focus on this point for now, because it's also very easy for a computer to identify that this point is in the convex hull. And the reason for that is because this point has the lowest x coordinate. If we look at the x positions of all these points, and we were to sort them by their x-coordinate, then we would very easily notice that this left point is on the left, and it is further to the left than any other point. And this is actually enough to guarantee that it is in the convex hull. One way that you could think about it is any part of the elastic band that starts right here has to hit this point. It cannot go past this point, and it certainly can't stop before this point either. So we now have one point that we know for sure is in the convex hull. And now we're going to use an algorithm called gift wrapping. Gift wrapping is probably the simplest convex hull algorithm. So we're going to start with this one point that we know is in the convex hull, and we're going to procedurally find all the other points in the convex hull. To do that, we're going to imagine this horizontal line, and we're going to look at this vertical line coming down from this point, and then we're going to look at all the other points. So we're going to look at this point, this point, this point, and this point, and this point. We're not going to look at any points that we already know are in the convex hull. And then we're going to go look at the most recent point in the convex hull. In this case, we still only have one point, and we're going to look at the line coming out of that point. In this case, the line is one we've chosen very systematically, but in later cases, we'll see that the line turns into something else. And then we're going to take a line from each of these points we're looking at, and we're going to think, what is the next point in the convex hull? And really, if we take all these points, the one that is in the convex hull is the one that has the furthest turn. That is this point. So one way we could tell this is it has the largest angle between its corresponding line and the line of the previous point. That is this angle. However, that's not one of the primitives we have. We cannot find the angle of two lines, or the angle around a point with two lines. Instead, we have a left turn and a right turn. So when we look at all of these lines, we can keep track of a maximum. And this maximum is rather easy to tell. We start with this line as the supposed maximum, and then maybe we look at this line next. And we check, hey, is this a left turn or a right turn? If it's a right turn, then that means we would prefer to take this line. So this is our new maximum. All right, and then we look at another one. Is this a left turn or a right turn? And it's a right turn, so we have a new maximum. This is our new maximum. And then we look at another one. So note that we're always starting at the current candidate point. So this is our point 1. And then we're looking at the most recent point that we know is on the convex hull, point 2. And then 3 is the current point that we're checking. Is this a better candidate than our current maximum candidate? So that is how we get this couple of vectors, essentially. This is where we get these 3 points, and this is where we get the left and right turn check. So we can check, is this a left or a right turn? We've already written code for it. So obviously, you might notice that this is a left turn. And so 3 is not a further angle than 1. It does not have a larger angle when we compare it to the original line. So our maximum point is still this one. Now we check another one, and we see this is a right-hand turn, and so it's a better point. This is our current maximum. And then we do one more time. We check, and we see this is a left-hand turn, and so this is a worse point, so we don't take it. So in the end, we now have an edge of our convex hull. We know that this point and this point are both in our convex hull. And in particular, we have an order on these 2 points as well. We have this point and then this point. And currently, because we are choosing to maximize right-hand turns, we're moving around clockwise in our convex hull. If we were to instead take left turns whenever we could, then we would be taking a counterclockwise cycle around our convex hull, and we would have had to start with this line segment, which isn't part of our convex hull. Note that the line segment we had before, the one that went down sort of like this, that was just a dummy line segment that we had in order to find this actual first one in the convex hull. So now we can repeat the process. This is the point on the top of our stack. And we do not look at this point anymore because it is already in our convex hull. So instead, all we do is we look at all the remaining points. And then we check. For each of them, left turn or right turn. Right turn. This is better than what we had before, which was our starting point. Left turn or right turn. Right turn. This is our new best possible point. Left turn or right turn. Not really a turn. So in this case, we actually have a few different options. If we want to include all possible points that are on the convex hull, then we actually look at whichever one of these points is closer. We don't have a primitive at the moment for Euclidean distance, so we're not going to think too much about this case, but it's certainly quite easy to have a primitive for Euclidean distance given the coordinates of all the points. It's just the square root of the sums of the differences of the coordinates squared. If we did want to include all of those, and say this point wasn't anywhere in our point set, then we take whichever one is closer to our current top of the stack, or the most recent convex hull point. And if we didn't want to include, then we take whichever one is further. And this way we always properly break ties, no matter which one we got. So let's say we stuck with this point. In this case, it's going to turn out that it doesn't matter, because we have this point. And in fact, this point will never be in the convex hull. So left turn or right turn. That's a right turn. So in fact, this point is better. And in fact, we've looked at all the points now. So at this point, we're almost done. Now that we're no longer on the first step, we just need to double check something. We need to double check that if we look at this angle, so we take the line from our current most recent convex hull point to our first convex hull point, we need to double check that it's still a convex angle. That is, this angle is a right turn. And in this case it is, so we know that we're not done. So now we move on to the next point, and eventually we'll see that we end up with this point. So our convex hull looks like this, and then we'll do that again, and we'll end up with this point, and our convex hull looks like this. And then if we do that one more time, we'll end up with this point, and that doesn't quite look right. What we actually want is an edge here, and that would mean that we should have stopped already. We shouldn't be taking any more points. So what happens when we find out that this is the best possible point to take is we look at this. So we have these 3 points. This is the one we were just looking at. So the most recent convex hull point just a moment ago. This is the most recent convex hull point, and this is the first convex hull point. And then we think about these 3 points, and we look to see if they form a left or a right turn. And we see that they form a left turn. And so this is not a convex angle, and so the point we just found isn't actually part of the convex hull, and we should have stopped. So that's what we do, and that's how we know that this point isn't part of the convex hull. So now let's actually go and implement gift wrapping. So gift wrapping is of course a convex hull algorithm, so it takes in a set of points and it outputs a convex hull, which is also a sequence of points. Now, if you remember, the first thing we do is we find the point with the minimum x coordinate, the most to the left point. This is, of course, as simple as iterating through the array and checking if the x coordinate of the current element in the array is less than the current leftmost element of the array. Once we've done that, we want to start by putting that leftmost element in our return values. This is going to be a bit weird. Even though I'm returning a list of points, I'm actually going to change it to be a list of integers. And these integers represent points, and in particular, they represent points in the point set. It's really simple to change between these. We can do this with 2 lines of code in C++, but it's a lot easier and nicer to do it this way, and possibly more useful in some use cases for this algorithm. From here on out, we're actually going to make a couple tricky changes that make our implementation a lot simpler. the first tricky change we're going to do is that we're not going to keep track of which points have been seen so far. So since we're not keeping track of which points have been seen so far, how are we going to make sure that we don't re-add some of the same points? The tricky part about this is the fact that I'm going to claim that if we are going to re-add any points, the first point that we would re-add is leftmost. And because the first point that we could potentially re-add is leftmost, we're just going to check, is the point we're trying to add leftmost? And if it is, we're going to stop. Because not only is it the first point that we could re-add, but right before we re-add it, we've actually got the answer. So we have all the points in the convex hull at that point. Let's start our loop. So our loop is going to keep track of the most recent thing that we've added to the convex hull, and it's going to check at the end, is that thing equal to leftmost? And if it is, it's going to stop. Inside the loop, we need to figure out the next point in the convex hull. In order to find the next point, let's just keep track of a candidate. Let's start with setting this candidate to be equal to the first point in our point set. There's a tricky edge case here. If point 0 in our point set is the current point, then we just want to ensure that we don't pick that. So we make sure that we skip over that. And then we iterate through all the other points in our point set. And so long as they're not equal to the current point. And if the turn that we have discussed is a right-hand turn, then we want to make that new point our new best possible next point. So remember, a right-hand turn is of course -1. If we were to change this to 1, then all we would do is we'd find the convex hull in the opposite order. So currently we're trying to find it in the clockwise order, but we could also try and find it in the counterclockwise order. It doesn't really matter. But once we do this, if it turns out that it is a right-hand turn, then we just need to replace our candidate next point. If the next point is equal to the leftmost point, then we need to break. Otherwise, we add this new next point to our return value, and then we change what the current point is. And that's the entirety of the gift wrapping algorithm. There's a couple different things to note about the implementation compared to what we had before. When we looked at the picture and we thought about starting with the leftmost point, we drew that vertical line down from the leftmost point. And we tried to compare other things to that vertical line. And then once we compared one of those things, we noticed that it was a right-hand turn. And so we ignored the vertical line from that point on. And we just used that new candidate next point. But it turns out that because we chose the leftmost point, and because it was a vertical line, any of the other points would have been preferable to that vertical line. And so we could just skip over the vertical line entirely, and on the leftmost point, we start by picking just a completely arbitrary candidate next. Since we're trying to find the maximum value, it doesn't matter what we choose. So we choose next equals 0. If that has a conflict, we change it to next equals 1. But the only important thing is that we choose a point that is not the current point as a candidate next point. And then we iterate through all the other points. And just as long as they're not the current point, we can do this winding calculation. And if it's equal to -1, then we have a preferable point. And a very important thing to note about this line is that it's not handling the case of the winding being equal to 0. So in this case, I'm assuming that the point set given does not have any collinear points, or that we do not care about collinear points. This isn't necessarily an assumption that you could always make. Sometimes you need to implement this slightly differently. So you'd have to handle the case of the winding being equal to 0 and check the distance of the two different vectors. That is the vector from next to cur and the vector from cur to I. And once you do that, you might be able to tell which one is closer. And so you'd be able to tell which one you should include or shouldn't include if you include collinear points or don't include them. And again, whether you include them or not is completely dependent on the application of this problem. At the very end, the other tricky thing we did was, in order to determine when to terminate, we actually just check if the next that we've chosen is the leftmost point. This is different from what we did before, where we checked if the next we have chosen forms a concave angle with the leftmost point and the point right before it. Either one works, but this one is nicer to code because it doesn't require us to check which points have been included in the convex hull already. And that allows us to keep track of a little bit less data. Now, one last question we have to ask ourselves is, what is the runtime of the gift wrapping algorithm? So given all these points, we iterated through all the points once in order to find the leftmost point, which takes O of n time. And then we started at the leftmost point, and then we iterated through all the points again in order to find the next point. And we kept doing that. We iterated through all the remaining points to find the next point, and so on. So in order to determine the runtime, how many times did we do this? Without too much thinking, you might be able to realize, of course, we didn't do it more times than we have points. So the runtime of this algorithm is upper bounded by n squared. And in fact, there are sets of points that could take n squared time. The examples of such points are convex polygon. These can have n points, and each one of them lies on the convex hull, and so you need O of n iterations. And so there's a lower bound of n squared. And normally, this is where we'd stop, and we'd say we have an upper bound and we have an example that causes that upper bound to happen. So this is the runtime of the algorithm. But in computational geometry, we go a little bit further than that sometimes. We do something called output sensitivity. And what output sensitivity means is that maybe this big O bound, one of these values, can be replaced by something involving the output. And in this case, we're going to use h to represent the number of points in the convex hull. And of course, h is upper bounded by n, but it's not always equal to n. In this example, there's 5 points not included in the convex hull, and there's 5 points included in the convex hull. So h is half of what n is. And in fact, h can be arbitrarily smaller than n. If we take any point set, and then add 3 points, forming a triangle around all the other points, then suddenly there's only 3 points in the convex hull. So h can be very small compared to n. It's not always very small compared to n, but it can be. And so maybe it's a little more precise to describe the runtime of this algorithm in terms of h. And I've already written it out here, but the runtime of this algorithm is n times h. And that's because the number of different times we take these O of n routines is equal to the number of different elements in the convex hull, because each one of these routines finds something new in the convex hull. This first one finds the leftmost point, this one finds the next point, this one finds the next point, and so on and so forth. And so the real runtime that we care about in computational geometry is often this one.